All right, here we have our setup. We're running Cinebench R23 as our benchmark. So for my CPU, I have a 6-core Ryzen processor, which means that there are 6 mini processors within the overall processor. And this test, Cinebench R23, I can set it to single core mode, which means that it will only test one of those 6 mini processors within the overall processor, which in turn creates less heat and draws less power for our tech to try to cool, because our tech is only rated at 65 watts. So that's all the power we can pull from the CPU with the tech still being able to cool anything at all. And we also have hardware monitor pulled up as our CPU monitoring software. That's monitoring voltages and wattage and temperatures. Right here you can see where the thermoelectric cooler is connected. It is in between the large heatsink and the CPU. And over here is the actual where the tech is being powered from. That is a 12-volt battery being charged while also being connected to the tech itself. Since we are drawing power from the battery's voltage would go down if we weren't charging it. And that's why we're charging at the same rate that we're pulling power out of the battery, to keep the battery's voltage at the same for the entire duration of the test. This is our thermal paste that we use as our known good thermal paste. This is Arctic Silver 5. It is a industry standard for thermal pastes. This is our thermoelectric cooler. This is what it looks like without being in there. First thing that we tested was Nutella, and this performed surprisingly well. And the other thing that we used was toothpaste. Here you can see it with some of it on the thermoelectric cooler. So in between each run, we would completely clean off the thermoelectric cooler and then reapply for each run. This is what it looks like with the Nutella on it. And there's the toothpaste. So before starting this experiment, none of us really knew exactly what was going to happen. Me and Zach had seen the Linus Tech Tips video where they had done a whole bunch of different thermal paste with things like mustard and Nutella and toothpaste and peanut butter and a whole bunch of other stuff. But none of us really knew exactly what was going to happen. I thought it was going to overheat almost immediately, just because the thermoelectric cooler is not the greatest cooler out there, and it has a maximum of 65 watts. And I knew that my CPU pulled more than 65 watts at its maximum, so I tried to downclock it to fit within our heat dissipation parameters of that 65 watts. But I still had zero faith that the thermoelectric cooler would be able to cool the CPU at all. And this is the data that we got after we had completed our runs. The first line is our benchmark, so our control. That is with the Arctic Silver, our known good, on the hot side of the thermoelectric cooler. And we started out at a temperature of 31 degrees, but we never went above 32 degrees in testing. We tested it for over 10 minutes and never went above that. For the Nutella, we started out at a temperature of 30 degrees, and it quickly spiked up to 36 degrees, but then leveled back off at 35 degrees. For the toothpaste, it started out a little bit cooler. I think we let it cool down a little bit too much while it was idling, but it started out at 27 degrees and it only got up to a temperature, the max temperature of 29 degrees, but it leveled off at about 34 degrees after about 8 minutes or so. And then I also did some calculations based on this. I tried to calculate from the CPU die to the air that overall thermal resistance, and that ended up being approximately 0.275 degrees Celsius per watt. This was averaging our approximate wattage from the CPU at about 40 degrees Celsius, and an average delta T, our average change in temperature from the CPU to the air at around 11 degrees. This is for the Arctic silver that hit 30, that only went up to 32 degrees. And that number was approximately 0.275 degrees Celsius per watt. And I also went ahead and did a quick thermal conductivity calculation and used our 40 watts as our steady state power draw. The total, so L, the total thickness between the CPU die and the start of the main CPU cooler, where we are assuming it's common air temperature. For the area, we used a 35 millimeter diameter circle instead of the whole 40 by 40 because the actual thermal paste that we used, all of them, they didn't completely spread all the way out to the edges of everything. It was about what we assumed, but it's not perfect. And then for the delta T, this is again for our control, and I used our delta T of 32 to an air temperature of 21 degrees. And that comes out to a total of 20.72 watts per meter Kelvin. For the Nutella and toothpaste calculations of thermal conductivity and thermal resistance, we only needed to do a single one because the change in temperature between air temperature and CPU die temperature was the same for both of them, making the overall calculations the same. For our thermal resistance, we have a delta T of 14 degrees Celsius. That is our 35 degrees on the CPU core to an air temperature of 21 degrees. And then our Q dot is our same average wattage from the CPU of 40 watts. And that comes out to a nice 0.35 degrees Celsius per watt. For thermal conductivity, our Q dot, L, and A all stay the same as the control. And our delta T just goes from 11 degrees Celsius up to 14 degrees Celsius. And that, after running through those calculations, that ends us at a thermal conductivity of 16.63 watts per meter Kelvin. Now, we did want to get more granular with these calculations, but that would have involved us making a lot more assumptions in these that would not have been conducive to a correct answer in the end. So we decided to just forego all those calculations and just do one overall thermal conductivity and thermal resistance calculations for our three types of our three types of thermal interface material. Looking at our data from the Nutella and toothpaste tests, we see that the Nutella almost immediately jumps up to 35 degrees Celsius, while the toothpaste takes over 3 minutes to get to that same temperature, but they level off at the same temperature, meaning that more than likely the toothpaste has a higher heat capacity than the Nutella, but they have the same thermal conductivity because they can reach the same temperature difference in the same, or with the same heat flow rate going through them. Neither of these solutions would be good long-term solutions though, because the Nutella has sugar in it, so that sugar is probably going to eventually burn and become very dry and lose its good conductive properties, and the toothpaste will probably dry out the same as the Nutella will. So these do not make for good long-term solutions, but will work in a pinch if you absolutely need them.